Thank you for joining us. And when we get started here too, please feel free to ask Mark any questions related to the information or any other questions in the HVAC industry. Mark is a really valuable resource, been around a long time and has a lot of experience. Hey, Cully from Baton Rouge, Bob from Atlanta, thank you for joining us. We'll get started here in just a minute. Joshua Berard, good morning from Raleigh. Hey, Josh, thank you for joining us. We appreciate you. Got a well-rounded travel in the globe here. And John is in Sacramento. Thank you, John. Gabby from Maryland with Green Building Engineers. Welcome. Kristen Sussman from Charlotte. Welcome. Anand is working as an HVAC design engineer in Louisiana. Thank you. Okay, all right. I see my timer's coming to an end, so I better get my act together here, Mark. Hold on a second. So, all right. So we are going to get this thing going here. Give me just a second to get these screens figured out. Okay, thank you all again for joining us, and we're going to go ahead and get this thing going. So, okay, welcome to the Engineers HVAC podcast, where we strive to give back to the HVAC community by sharing our HVAC application and design experience. Today, we are excited to bring you episode 31, a live recording, which we're streaming on LinkedIn. I'm Tony Mormino with Insight Partners, and thank you for joining us today. Our guest for this episode is the one and only Mark J. Fly, PE, who has over 40 years of experience as a researcher, consulting engineer, contractor, manufacturer in the HVAC industry. Currently, he serves as the executive director of the Norman Asbjornson Innovation Center and Laboratory at AAON, Inc. in Tulsa, Oklahoma. In ASHRAE, Mark holds the grade of fellow and has been honored with the Distinguished Service and Exceptional Service Awards. He has been and is currently active on numerous technical committees, standing committees, and councils, serving on the Publishing and Education Council and as a trustee on the ASHRAE Foundation Board. He served as a director at large on the ASHRAE Board of Directors from 2014 to 2017. He has also been active in the HVAC Industry Trade Association, AHRI, serving on the board of directors from 2012 to 2016 as section chair for unitary large equipment and air-to-air energy recovery. Mark has also participated in the AHRI Technical Committee on Sound and the Unitary Sector Leadership Council. He is currently serving on systems steering committees. Wow, I'm exhausted just reading that. That's a lot of stuff. And what that tells me is Mark's a big deal in the industry, so please ask questions. This is a great opportunity if you have any. The title of today's presentation is Pushing the Boundaries of HVAC Efficiency. We're going to look at the current technology and what's next. What do we need to do to increase efficiency? So Mr. Fly will share his insights and on the challenges associated with regulations, their compliance metrics, and how they often manifest unintended consequences. I think we've seen a few of those. As we strive to lower building energy and carbon consumption, we must raise the bar on energy efficiency. In this presentation, Mark will discuss the future development of performance maps for all types of equipment and the better incorporation of control and operation sequences into modeling software. Ultimately, the goal is to reduce the whole building energy and carbon use, which requires the reliance on whole building energy modeling combined with continuous commissioning to ensure continued efficient building operation. We encourage questions and would love for this to be interactive. So please put any questions in the chat. We will gladly respond. This does qualify for PDH credits. So please email me. I'll put my email up here in a minute. And you could also, if you're watching this on YouTube or listening on our podcast in the future, you can always find my email address in the description of the video and or podcast. Mark has also shared his slide deck with us, so please email me if you'd like a copy of that. This recording will be available on our podcast called the Engineers HVAC Podcast, and there is a QR code in the upper left corner if you would like to connect. And we are thrilled again to have Mark Fly join us today and share his experience in the HVAC industry. So please sit back, Relax, enjoy this insightful and informative discussion on pushing the boundaries in HVAC efficiency. Okay, so I'll turn it over here to Mark, and I can't wait to see what you have to share with us today. Let me get my screen shared here. Give me just a second. Okay, thought I had that ready. Sorry about that. Okay, take it away, sir.
Okay, since you've read all that, you've said everything I need to say. So. No, but I got a few graphics to make a point, right?
Oh, good.
So yeah. So just kind of an introduction. Most of this presentation came from information that I've been involved with on the HRI System Steering Committee, which got started in 2012. So we've been running a little over 10 years now, and we've made some progress, but not a lot, because this is going to be a really slow process. I was telling Tony earlier, I'm not sure that I'm going to be around to see the end of it, but I think this is really where we have to go, because we're kind of maxing out. So let's kind of just jump into if you'll flip to the next slide, Tony.
You got it. And when you say see the end of it, what is the end game? What is
Well, it's really we've got to change the way we think about energy efficiency and rating equipment. I mean,
gotcha.
So I mean, obviously, decarb and building energy efficiency and global warming, and these are all the hot topics right now that are going on,
mm-hmm.
and lots of discussions in the industry. So, and obviously the best way to save energy is not to use it in the first place. So anything that we can do with efficiency and conservation is much better than whatever we have to do on the production side of energy. But what we've seen a trend over a number of years, but actually since lighting has made such great gains with LED lighting and better lighting controls and everything else, now HVAC is the predominant energy user in a building. So so basically 44% of the commercial energy consumption is HVAC systems. So
hey, Mark, are all buildings using LED lighting primarily?
No, I don't think they're all are, but there's a lot of retrofit. There's a lot of that going on, and it's you can't go buy an incandescent light bulb anymore. So
right.
Incandescents are gone, and the high pressure sodiums for plant lighting, a lot of that stuff's getting replaced. Those like a lot of technology, as the science evolves, it gets more economical, less expensive, and immensely cheaper to operate, because LED lighting has just revolutionized the amount of power that goes into lighting.
It is amazing, an amazing technology leap, that's for sure. And we were talking about this we had a decarbonization. I know you're going to get into it. I'm not going to get into a lot of that now, but someone was commenting about, they did a LED lighting retrofit in a high-rise in a very old high-rise in New York City, and they had a huge problem because now they didn't have enough heat in the building.
Right.
They had to supplement to put a new heating source in there somehow, which is not cheap.
And that's what part of the discussion that's going on in some of the rating systems. All HVAC equipment's standard indoor conditions 80-67. 80-67 came from 75-degree room, 50% relative humidity, and some heat gain off the fluorescent light ballast and the ceiling plenum. It's kind of a mixed air temperature without a lot of outside air. So I'm not sure that any of those things apply anymore. So,
right. I hear you.
So, yeah, we have dropped a lot of heat into that return plenum, but we've added a lot more outside air. So it kind of depends on what season, and we're going to talk a little bit about that. But the important thing is, HVAC is a big deal obviously in any kind of decarb or global warming discussion that we want to get into, or if we want to have net zero buildings. So,
yep.
Let's go on.
There you go.
So one of the things that I've kind of, like I said, I've been around for 43 years now in the industry, and kind of started out in energy modeling and energy studies back in a energy crisis that happened in the late 70s and early 80s, called the Arab oil embargo, when the Arabs turned the oil off to us. So I mean, if you watch what happens, we put in regulations, we put in rules, we put in ASHRAE standards, we put in guidelines, because we're trying to drive the behaviors that we think will do what we want them to do, but a lot of times when you do that, there are these unintended consequences associated with them. And one of the things that happens in HVAC equipment is, because we want these single number rating systems, we want to say, well, what air conditioner is better than what air conditioner, or, is this better than that? Then we've really simplified these things down to a point that they don't tell us a lot about what's really going on with in the building, or how they're actually used. So
they don't tell us the whole story of that.
They don't tell us the whole story. SEER, right, and IER and IPLV for chillers. Those are things that you can say, okay, if I'm looking rooftop to rooftop and I'm looking at IER, this one is more efficient than that one, at least at those 4 points that's based on. So right. And those 4 points were picked, and they're kind of this they're very U.S. centric, so it's a blending of a bunch of cities in the United States, which means it doesn't line up with anywhere. Actually, I think it's interesting if you look at the design conditions, that we test at 90, 80, 67, 95. 95 degrees about the design temperature for Atlanta, Georgia, and Washington, D.C. So, right. The headquarters of ASHRAE and the capital of our country seems to be what set our rating system.
That's the rating system. Yeah.
Our rating system. So we have these simplified metrics. We also want to make sure everybody's following the rules. And so we want to crank down the uncertainty on these metrics and measure things very accurately. And a lot of this stuff is hard to measure. I mean, when you're looking at especially moisture content in air, what's your relative humidity, what's your wet bulb temperature, what's your humidity ratio, however you want to express that. That's a difficult quantity to measure and calculate with any great degree of accuracy. Today, we still pretty much use the technology of a wet cotton sock on a thermometer to measure humidity. That is the most accurate way to do it today.
That's wet bulb if you're new to the industry.
That's wet bulb in case you're new to the industry. That's wet bulb temperature. We used to sling them around on a thermometer with what we called a sling psychrometer, do this.
We did it last time we did a presentation on that. Someone posted a picture of a sling on our
sling psychrometer, and everybody think that's kind of, that's old and out of date. Well, that is way more accurate than any relative humidity sensor, solid state relative humidity sensor you can go out and buy.
Interesting. I didn't know that.
And so in our lab inside the chambers, we have a high precision RTD that'll measure, hundredths of a degree, but it's got a cotton sock sitting in a pool of distilled water and a fan blowing over it to measure wet bulb. This is state of the art lab things. And we're, we'd all like to go to, and actually that's kind of a pain to maintain and work. And all the techs have to change their socks every morning, right?
Right.
Put new cotton pieces on there because we don't want to get dirty and,
run out to the store and get a jug of distilled water.
Go get it. Yeah, we buy it in 100-gallon totes. So it's so anyway, there a lot of that technology is. I mean, these things are hard. So if we crank things down to really tight tolerances, which is really tight tolerances, by the way, is 5%.
Right.
But
right.
if we want to maintain at 5%, then we have to do a whole lot of testing to make sure we maintain it in 5%. You know,
Mm-hmm.
we have to do a lot of sample testing. We have to do a lot of, you know, because there is some data scatter, there's some production variations, there's equipment variations in all components. So that involves a lot of testing. And because we're trying to do all this testing, get the accuracy really high, it means we can't test a whole lot of points. So one of the kind of dirty little secrets in the HVAC industry, if you look at any kind of piece of equipment, I don't care if it's chillers or especially on the refrigeration side, any of the HRI certified equipment, we usually know a whole lot at 4 data points, at 4 distinct data points. You know, for IER, it's 25, 50, 75, and 100% load at 95 degrees and some declining temperatures and humidities past that, right? Mm-hmm. But we don't know a whole lot about what our equipment, we really, quite frankly, don't know what our equipment does a lot outside of that, because those are the data points that the whole industry has been so focused on to keep together. So,
I'll be darned.
So that's kind of that unintended consequences that we've got.
Right.
If we go to things that are more flexible and more data points, we're probably going to lose some of that insert. I mean, our uncertainty is going to grow. It may not be 5%; it may be 10 or 15%.
Mm-hmm.
You know? So you know, one of the questions is, can everybody accept that? You know,
right?
Can we do that? So let's flip over to the next one. So if we kind of look at blow that up a little bit. There we go. It's focusing in, at least for me. If we kind of look at the history of
how's that, Mark? See that? Okay?
Yeah, that's better. So, okay. and this is a little bit older slide, but it kind of follows. This is the 90.1 energy efficiency over time. This is what we progressed since 1975, basically when the Department of Energy got created, to today. And you can see there's this kind of straight line, especially since 2000 or early 2000s. It follows kind of the same slope of line as we go. But you're also kind of noticing that things are kind of flattening out. Now, mm-hmm. Pop the next slide up and we'll talk about some different type of equipment. And the y-axis is this energy use index, basically, you know, what's actually happening in the world in buildings as best as can be put together. And mm-hmm. So if we look in the residential market, and, you know, probably 80% of the HVAC in the world is grown in the residential market, you know, we made some big gains in the 90s because, quite frankly, our equipment wasn't, you know, that's when everybody got on the energy efficiency kick. And so, but you'll notice that the impacts that we're making in the last, 25 years, haven't really been that much. It's really
in the last 25 years.
Yeah.
Which would be, I'm going to try and circle this. That would be this area here.
Well, I mean, that's up to 2035, but I mean, well,
that's the future. I circled the wrong thing.
Future,
I got you.
Right.
I got you.
Yeah. But, it's been relatively flat. And so there is, depending on the type of equipment, let's flip through a few others because I've got some other type of equipment on here. So,
there's 3-ton residential.
There we go.
10-ton rooftop right here.
So 10-ton rooftop unit there again, we probably didn't get to the higher efficiency, and this is really kind of the highest efficiency equipment on the market. It's kind of what's represented here.
In this purple line here.
This purple line here.
Which I'm going to track like right here. Okay, gotcha.
Yeah, but if you kind of look at that, now we're kind of above what the intended effect of 90.1 was supposed to be. So, and the next couple ones are, pop the next one up.
Okay, so 3-ton residential, 10-ton rooftop, and then we've got.
And now we've got a 150-ton air-cooled chiller.
Right there, gotcha.
Yeah, and notice that in 2015, that's basically gone flat.
Yeah.
So
what is the dotted line there representing? Mark? Do you know?
I'm not absolutely sure because this is my slide. Maybe that's as good as we can get. I don't know, but
yeah,
I mean, one of the things that we talk a lot about in the System Steering Committee at HRI is that there is a theoretical maximum tech, or a practical max tech on this, and
sure.
Pop the last one up if you can go up to there's a water cooled chiller on here too.
There we go.
Yeah, so
water cooled chiller right there.
So the water cooled chiller, you can see we also took it's kind of tracked off of the air cooled chiller. Yeah. Both the chillers have kind of almost flatlined. So in chiller technology, we are very close to max tech. So if you look at a water cooled chiller today, if you look at the top of the line water cooled chiller today, the approach on the suction to leaving water temperature is close to 1 degree. The approach on the condenser side, the condensing water temperature to the saturated condensing temperature is about 1 degree.
Mm-hmm.
If you want another, if you want to get a half a degree, you're probably going to have to put 100 times more copper in that unit, and you got half a degree. You haven't increased the efficiency of that machine hardly any at all.
Right. So it's the law of diminishing returns.
It's just the law of diminishing returns. So if we're going to stay with vapor compression, unless somebody can, come out with the new LED light that is incredibly efficient at cooling air, so much better than we can with compressing gas.
Right.
We're at max tech. So,
right.
So where do we go from here? So where do we go from here?
Right. You're just talking about exchanging energy, and you can only, Mr. Owner, if you want this extra, 0.1% of efficiency is going to double the price of the machine. So you're at that point.
Double the price of the machine. And,
right,
and what, how are we getting, how much carbon are we saving? How much closer are we getting to net zero?
Right.
By doing that, we spent a whole lot of money. We didn't really get a whole lot of things out of it. Right. And
exactly.
And how much carbon did it take to mine all that extra copper that I had to put in there? And, so you've got this life cycle cost, this end use cost that you've put a whole lot more materials in there, and you really haven't got a lot of gain
yep.
out of it. So
I think we squeezed all the juice out of that turnip we can with the water cooled chillers.
So the next slide is even an older slide, but this was done by Pacific Northwest Labs, and you look at it, it was done probably 2015 or so, but the trend has been that it's the same slide, it's the same type slide track you've seen, but they projected, and a lot of us are talking about we want net zero buildings, and 2030 is a very popular one. Everybody'd like to do it quicker, but I mean, look at the slope of that line, and remember what that equipment looked like. That equipment's going to flatten out. And we've got to pick up the slope of the line. We've got to move forward from today. We've got to, and by the way, we didn't follow that line starting in 2015 either. So it's even a tighter slope. We've got to really pick it up if we're going to actually have some net zero savings, from the equipment side that we can drive from that equipment side. So I mean,
let me ask you this.
What this is telling me is that we can't get there from here.
We can't, right? I get it. So let me ask you this, because I, for me, it's all about the HVAC side of it. But like, we're getting picked on because we're the highest energy user. It's an easy target. Do the same like profound changes in efficiency and effectiveness of like the building envelope and the windows? Do all those also have the same kind of attention that HVAC gets? Because I only live in the HVAC world, so I don't see any.
Well, and I think they do, and I think we probably, there again, if we're, we can do some things with envelope losses, but I mean, it kind of depends on what kind of building you're looking at. In a house, modern residential construction, a lot of times they're going 4-inch foam walls. They're spraying foam in houses. We're getting R30, R40 walls, ceilings, so I make it a 6-inch wall and I make it R50. How much heat transfer how much have I changed? What have I changed in the grand scheme of things by doing that? In commercial buildings, we just went through a pandemic. We re-emphasized the importance of bringing outside air into a building.
Right.
So commercial buildings, it's not really the envelope load that's driving most of the load. It's the people and the outside air you're bringing in.
Right.
It's the internal loads. So we throw a lot of insulation in there, but what can we do otherwise? We're doing a lot of heat recovery. The heat recovery helps, so there are things that we can do, but and that's kind of part of the reason that we need to quit. We get so focused on just HVAC and comparing, how many watts does my LED light take? I can do a 100-watt light bulb with a 7-watt LED bulb. Wow, that's cool.
Right, because we're hooked up to the meter. We're actually pulling in the energy, so they're not Yeah, I get it. Yeah,
but
totally.
But if you turn that light off, it uses 0 watts. So if you leave all your lights on in your house 24/7, then no, you're not necessarily doing the best you can do, right? You're not driving.
You're describing my house.
Well,
unfortunately.
Kids, right? So
that's not really true, but I just to make that.
Yeah, but
anyway,
so
when you got teenagers, you have you have only so much control. So
right. You walk around the house, turn lights out all the time.
That's right.
So this is kind of the why. This is why we need to start doing something different, because just looking at EER, SEER, IER, IPLV isn't going to cut it anymore.
Got it.
So, and that's a big change. It's a big change in mindset for the industry. It's a big change in mindset for regulators. We have a lot of inherent mistrust among each other.
Right.
The energy advocates don't trust the manufacturers. The engineers don't trust anybody.
Right.
The owners all think that we're just all running the price up so that we make more money. So it's we got to cooperate and get this stuff going together. So
right, and if we can make the equipment, more efficient in a way that the ROI is there and it's not much more expensive, it's in our interest to do that. Like, we want to do that. That's what we want to do. Right. And I think our industry has done an amazing job of, it's very competitive, and many people may not understand that who are not in the equipment side, but we would love to have a piece of equipment that's minimally more expensive, but is way more efficient than the competition. I mean, that's like the holy grail of, equipment sales. So, it's really difficult. And especially today, it's like we've kind of maxed these things out. It seems. I mean, I'm sure there's more to get out of them, but you know what I'm saying. So
there's a little bit more, and if you kind of look at that future, if we went back a few slides and looked at future view on like unitary equipment, there's a few more steps there that can be made. But three or four more steps, we're going to be done. We're going to be at that point of diminishing returns, and we're going to be where the chiller guys are. Now, you just can't throw that much more condenser.
We're going to be flatlined.
Exactly. The equipment's getting bigger and bigger. It's getting more and more expensive. We're putting greener and greener and more expensive refrigerants in it. All kinds of. There's a lot going on right now in the industry.
For sure.
So, blow that slide up again. And this is some of the work that's been done in ASHRAE 90.1 and some other different part. And this slide takes a little explanation, but the blue dots and the red dots basically are heating and cooling load in a typical commercial building. And when I say typical, they're, 90.1 and the ASHRAE folks that have been working on this, and some of the laboratories and modeling guys that have been doing this, that have a multitude of different building types that they run in a multitude of different environmental conditions or climate conditions. And so I just kind of picked one that had it had superimposed on it an IPLV curve for a chiller, showing the design condition and the 4 data points.
Okay.
And where the building really operates at.
So let me break this down for a second. So on the x-axis, we have ambient temperature, which is going from 0 to 100.
To 100.
And we have building load, power consumption.
Building load, BTU.
Building load,
yeah,
BTU.
So
okay.
basically just BTUs per hour, right?
BTUs per hour, the HVAC load, basically.
Yeah, HVAC load, heating or cooling. And I picked this. Yeah, this one's for a zone 4, and I showed the zone 4 map. Zone 4 is yellow. That's that Washington, D.C., Atlanta, Georgia area right there.
So in the yellow area here is the zone 4. That
yellow arrow is zone 4. That's
gotcha.
kind of what, that's a predominant controller on, that's kind of the average of the country. It's moderate temperatures with humidity. I mean, basically, so if you go out west, you have less humidity, so the climate is different. But if we look at something that's got latent load on it, we got humidity on it, and you look at the place we rate this equipment at, the things that we drive the equipment to be most efficient at, is not where this equipment is spending most of its hours running. It's right at the borderline edge. Matter of fact, the design cooling point, which granted is not weighted very heavily in IPLV or the design cooling point in IER or SERIN weighted, but basically we're showing no hours in this particular building in this particular climate at that design cooling load point.
Okay, so the IPLV integrated part load value, for those who don't know.
Yeah. And then you see the green point, there's here. Right. And then on the other side, you look over on the other side, there's the design heating point.
Right. So we're
there again, way up there where generally you're not, and the density of the dots is basically depending on how many hours that you're running. That's what.
Right.
So.
And what this IPLV curve is showing is we're just barely touching the surface of it, and only at these 3 points, and the design cooling, which is 25% of the of the equation. If I remember my IPLV right, it's like way off the charts. So
it's way off the chart. So yeah. Now, can you pick a climate where that might be in the chart? Yeah, but but if you look at all these, and I've seen many of these charts, 20 one of the slides that I was looking to steal off of some of this stuff had 15 or 20 of these charts on there, but they all kind of look the same regardless of what you plot on there, and regardless of where you do it, it follows the same trend.
So you're not in the real world.
You're not in the real world, but
we're kind of guessing at it.
But our metrics, the things that we sell with, the things that our customers and everybody, the engineer designed to, I want an IPLV chiller at this point, are based on these 4 data points. So this is where we're driving that equipment efficiency. If I'm a manufacturer and I'm trying to make the best piece of equipment to sell my customer and want to sell that piece of equipment, want my customer to want me over my competitor, I'm going to design something that works really well at those 4 operating points, right? That's
we have to stay in business.
That's what we have to do.
Right. We have
and I've got a great one that runs, mid-pack down there in the middle, that there's no way for me to tell that story. I can't tell anybody who's going to believe me,
Right.
Just, hey, just trust me. Right.
Right. It kind of reminds me of when the digital compressors first came out, and it was hard to show the credit you would get at part load for the part load energy usage. Right. Cause it didn't care that it was unloaded half the time, because it just looked at the impact it had at when it was loaded. And
right. So there's some things here that could be improved. Now, when we started doing this, rating this equipment, which goes back about 65 years, is when we first started rating equipment. Maybe it couldn't be improved. That was probably good data back then. We didn't have, 65 years ago. I mean, I've been in the business 43 years, and I feel like I was like the first of the computer generated I learned how to use a slide rule, but I was never very good at it.
Right.
So I was the first of the calculator cripples, what we used to call it, what our professors used to call us, who all were slide rule guys.
Mm-hmm.
So
they made fun of the calculator guys.
They made fun of the calculator guys.
Right. Look at that calculator. Gotcha.
Look at that calculator. You're not doing real engineering using that machine, right? And now no one uses a machine; they all use a spreadsheet, right?
Right.
So those 4 operating points, 45 years ago were probably state of the art, but we haven't really moved past that. So
gotcha.
So wow. So I think as far, in my opinion, and part of the point of what I try to tell people is it's not that we're making bad equipment. We're probably making the best equipment we can make, or we're getting very close to that. What I don't think we do a great job of is what we do with the equipment, how we operate buildings. I think we get pretty sloppy in that.
Yeah.
And how we operate the building, and even to a certain extent how we operate the equipment, because we've been so focused on these 4 data points, we really haven't given a lot of thought or done a lot of testing or done a lot of research into what happens down there in the dark blue part of that cloud, or the dark red part of that cloud, where all the time's being spent. How much improvement could we do there? Because that's what really matters. That's where you're going to save that's where you're going to save the carbon. That's where you're going to save the energy. That's where you're going to lower the people's utility costs.
Because that's where we're living.
That's where we're living. That's where life is. So
what do we need to do to make that happen?
So I don't remember how many more slides I got on why. So I have to keep going. Okay. So all right. What do we have to do to make this happen? So, so basically we live in like I was talking about, we live in a data rich world. We can be data rich. We have so much data, we can't look at it all. Right.
Right.
I tell people, I give lab tours when I'm in town at our lab. We have 200,000 data points in our lab. Gosh. You think anybody can look at 200,000 data points? But I can record them.
Not sure what to do with them, but we got them.
Sure. Right? I mean, a lot of them is thermal mapping and stuff like that. But but we live in a data rich world. What we got to do is learn how to use that data. So we need to do that paradigm shift and get away from this product performance and get to this building energy performance. And so we're living down there in that product performance green highlighted band of that pyramid.
Right.
And so what we need to understand is, what are our energy needs? What do we need to run the buildings? What do we need to run the world? How are those used? How do those needs get met by equipment? And then at the end of the day, what we're striving for is, how do we make buildings that burn less greenhouse gas, use less carbon, right? That's the goal.
That's the goal, right?
How do we use less energy at the end? So, what we do know is we know quite a bit about part load efficiency, about full load efficiency. We know 4 good data points on part load efficiency. But we don't know much about this performance mapping. And I say that, but there has been a shift. And one of the things that has been accomplished in the last 10 years is for chillers. Chillers, when you go get an HRI certified chiller, even though if you pull it up, the certification certificate has the IPLV, that's not what's certified when you certify a chiller. What you certify when you certify the chiller with HRI is you certify the selection software. This is a new trend. So HRI has that selection software, and you can email or call HRI and say, hey, I'm selecting this chiller at this crazy data point. I want to know what the capacity is. It's 65 degrees outside. I want 62 degree leaving water temperature with 75 degree entering water temperature. I got this weird outside the realm condition that's not on the IPLV point that I got to have for my building for whatever reason, right? and their selection software lets me get a capacity and an efficiency at that point. You can call HRI up and say, hey, is that a certified point? And they can run that software because they have that software. They have the certified copy of the software at HRI for that chiller. They'll run that software and come back and say, yes, this matches what the manufacturer told you. This is a certified point. So
they have the manufacturer's current version of their selection software, basically.
Their certified version of that. I'm saying certified because it should be the current version. If it's not,
gotcha.
That's how you get caught, right?
Gotcha, right. So they have the current certified version. Yeah.
So if I certify a chiller in my lab, and we've done that for a number of years and done it for some other people, they do the IPLV points and they do what they call a random point. Anywhere picked that your software will select, I guarantee you'll be in a corner. It will be that weird. Yeah. Hey, you said this thing would do 75-degree leaving water temperature at 35 degrees outside, and 90-degree entering water temperature. So anything you can select that you'll get a rating, you'll run that point. You fail that point, you fail the test. You re-rate everything every rating in your software by whatever percentage you failed that test by.
Wow.
So yeah, this is a big deal.
What is this new, Mark, or have I just not known this? Is this been around a while?
This has probably been around 5 years.
Okay.
So the other kind of interesting thing about chillers is, there's one HVAC product that is not federally regulated, and that's chillers. The U.S. government, the U.S. Department of Energy does not have the authority to regulate chillers because it got left off the list in 1975 when the Energy Policy Act was written.
Interesting. Okay.
And it has not been fixed since because we can't pass a law in Washington, D.C. So anyway.
Now that's not new. That's for
sure. That's not new. But the interesting thing is the only thing that we've got some other things now, but the only thing that's federally regulated that has mapped ratings, broadband ratings of different points, is the one thing that is not regulated by the U.S. government.
Gotcha.
So, anyway, so let's move on and talk about it that in a little different way. So if we kind of look at this, we're basically at this level 1. Up to level 3 level. Used to be all the equipment was certified and rated at EER, full load efficiency. So we've gone from 1 point to 4 points in 25 years, right?
Right.
Which is better. There's no doubt about it. As a matter of fact, the U.S. Department of Energy didn't recognize IER till 2013. Because I was on that when they started federally regulating it. We talked them into doing IER instead of EER because they can only regulate 1 point. They had to pick one.
Gotcha.
So once we go past that, then we need some more tools. We need more data. We need more models. So we need to understand this, regional annualized metrics. Basically we can't say everything has to be rated at this one HRI set of conditions, because that piece of equipment that operated best in Miami, Florida probably does not operate best in Vancouver, Canada.
Right.
Because latent conditions, temperature conditions are just different. So we have to bring regional metrics into that, and that's kind of that subsystem approach. We've started doing that nationally with SEER for residential equipment because they're regional standards. They're you have hot and dry, you have hot and humid, you have cold. There's different regions and different SEER levels that are available for those, so that you can have where your SEER rating is more restricted in a hot, humid environment where the HVAC load is the highest, so the building energy going to be consumes the highest. Whereas you could live with something a little bit less in Nebraska, but maybe your heating efficiency needs to be more efficient because it's going to have more of a heating load. So we've started doing that on the residential methods. Now, quite frankly, from a manufacturer standpoint, it's a nightmare because I don't want to have to get involved in bootlegging units from Minnesota to Texas.
Oh my gosh!
Because then how do you control where stuff goes, and how do you control?
It's crazy.
I built the Texas edition. I built the Vancouver edition. I built the Florida edition. So that's kind of a nightmare. But
we did
you could regulate it that way. You could do it.
Yeah, our last podcast we did was on the new SEER2 and EER2 and HVAC2, and I set it up. So I gave myself, a week or two to kind of put it together because I was unfamiliar with them. And about halfway through it, I was like, oh my gosh, we need to cancel this. This is way too complicated. I don't know if I'm able to explain it. And so I did the podcast, and I asked a couple people, what do you think? They're like, I think I'm calling you when I have a question, or I think I'm calling the manufacturer. It's just so confusing. And for the, I can't even imagine for the contractors and engineers how hard that is to keep track of. But
yeah. So
anyway.
So, really, if we want to maximize the potential of the energy savings, we need to get away from these prescriptive measurements and say, okay, when we put whatever equipment you choose to design or build in whatever type building, how many BTUs per square foot per year or how many kilowatts per square foot per year are you using? Right.
A whole building approach.
How many kilowatt hours per square foot? The whole building approach. So, and give the engineering community, gives the manufacturing community. We need to do a group hug, work together on this, and give us some flexibility, because everything in engineering is always a trade-off. You're always trading something for something else. Do you want efficiency? Do you want controllability? Do you want, back in before my time in the 60s, people were designing buildings that, it was really important to have thermal comforted buildings. Still is really important, but that was the most important thing. Energy was cheap. So what do? We cooled all the air down to 55 degrees, and then we put reheat coils in there and heated it back up to keep the temperature space. Great way of doing temperature control. We still do it in certain applications.
Sure.
Especially in laboratory environments. That's exactly what happens in my environmental chambers when I have to hold temperatures for plus or minus half a degree for an hour to do one of these 4 data points.
It works great.
It works great.
Dry the air out and heat it back up.
Dry the air back, heat it back up, add humidity where you need it, and then you can control it. So if that's the most important thing for you, that's what we do. But let's give people the flexibility to do what they need to do to get there, as long as they maximize and optimize the energy efficiency. So really what that means is we've got to make this fundamental change in our energy policy, the EPAC, how we do codes, how people think about it,
Right.
And it can't be all this adversarial that, the manufacturers are all out to cheat the public, and the energy advocates are trying to run all the hate manufacturers, and they're trying to run us all out of business. We can't keep that attitude up anymore. If we're really going to move forward, we got to work together on this. So the prescriptive things will shake themselves out if we ever got into the world where we had accurate building models. Why would there be any reason to rate a piece of equipment? Because if you can't put that equipment on the building and make the building work, no one's going to buy it.
That's right.
So let's make things that work. That drives that desirable effect of let's make equipment that's efficient in that blue cloud, not at the edges. So you have to start looking at this. Right now, we're operating in that red circle. If we look at a rooftop unit, we're looking at a fan, a coil, a filter, and a box with a compressor and a condenser section on it. We don't look at the economizer. We don't look at heat recovery. We don't look at what we're doing in the space. Are we doing VAV boxes? Are we doing reheat? Are we doing perimeter heat? So as you go to these different levels from level A to level B, then we get, okay, now we got everything in the unit. Level C, maybe we've got the occupied space, and then level D really, which isn't really shown here, is what's the whole building doing?
Right.
Are there other things going on in this building? We're also heating hot water. We've got lighting. We've got other things. Are there other things that we can integrate into this that affect how we operate and the best type of HVAC equipment we can put on there, or how we operate that equipment and everything to be at optimal? So just doing the same thing for a chill water system today. Looks like my red circle's a little off, but right, we got one chiller. You know, a lot of chiller systems, usually you have a couple, because
that's right.
One chiller goes out. I mean, you got one chiller with one compressor and it quit. Centrifugal chiller, it quits. You got no cooling in the building. Nobody really likes that.
Right.
You know, and the usual rule on, the rule of fans and the rule of thermodynamics are that, if I have two and I lose one, I'll probably get at least 2/3 of the capacity after the rebalance, right? Because the space going a little bit hotter, but my equipment's going to get a little bit more efficient because I'm working against a hotter space.
Mm-hmm.
Probably the thing in chillers that we don't have good understanding are what happens in that cooling tower. There's the cooling tower. There aren't IPLVs for cooling tower part load efficiencies. They're just kind of things that run water and have fans.
Mm-hmm.
Not a lot of attention paid to it, but you still get that same level. The other levels, then we have to take in the air handlers, and then we have to take in again.
Right.
So,
the cooling towers don't get a lot of love. That's for sure.
They don't get a lot of love. So,
right.
So how do we get there from here? Well, first it kind of goes back to building energy modeling, and Energy Plus which used to be called was DOE's code-based system that goes back, to the 70s basically, and they have several of their evolutions. They have a thing called Open Studio. Most energy calculation software is based on Energy Plus. There's been a lot of work on that on buildings, but the equipment side of that is sorely lacking. The equipment side basically are building equipment models that came from the 70s. Mm-hmm. And really haven't changed. So ASHRAE's been working for several years, and the standard's now out, called ASHRAE Standard 205, which is this technique to map building performance, kind of like I was talking about with chillers, have the whole map. So how do we do that? And I'll talk a little bit about that. There's other things like, how do we integrate Guideline V? HRI Guideline V is, if we put heat recovery in a rooftop unit, how does that affect the rooftop unit? So we don't want to get into the situation where what happened in 2013 when DOE started regulating HVAC. That drove a lot of industry interest. I was up there. There were most of my peers were up in DC talking to the DOE lawyers.
Mm-hmm.
Because when they decided that, hey, we have the authority, we're done with incandescent light bulbs. We've done that. That was part on the EPAC list in 1975. We've done with motors. Now it's time to tackle HVAC. And so the Enforcement and Compliance Division was, one engineer, one administrator, and about a dozen lawyers. So they're taking.
That's perfect.
Well, I mean, it's the truth.
Yeah.
And so we're taking industry practice, and we're going to write it into law. So, well, who does that? The lawyers, right?
Right.
They put it in the Federal Code of Federal Regulations. They made a minor change. They said, okay, we need you to certify and test. In HRI, we work on what we call basic model groups. Basic model group is compressor plus or minus 5% capacity, a condenser, and a condenser coil square foot area. So basically what it does, it means a basic model group is a tonnage. So a 3 tons, a basic model group, a 2 ton, and a 10 ton, and a 15 ton. Every tonnage you make is a basic model group. HRI tests 20% of your basic model groups every year. So in 5 years, they test one of each tonnage you make.
Mm-hmm.
Now, in that tonnage, in that 10-ton rooftop unit, I might make one with a 6-row coil or a 4-row coil or a 3-row coil I might have variable speed compressors. I might have digital compressors, might have on-off compressors. I might have ECM motors on my fans, or I might have belt drive motors. So I could have hundreds of different combinations and permutations in there. And if I list all those with a different energy efficiency, HRI will randomly pick out of that group. I don't get to say which one they pick. They'll pick one out and they'll test it. So well, what DOE said is a basic model group is any unit that has any different energy efficiency than any other unit. So all those combinations and permutations came on the table, right? So I sat down and did a calculation and came up and said, well, best I could tell, my company AAON had 6 trillion basic models. And we're not exactly sure how we're going to test any significant percentage of that in any given time. And so I went to the meeting and stood up and said, I have 6 trillion basic model groups. and my good friend, Dick Lord from Carrier, who's done a lot of the work that a lot of these slides I've stolen from Dick. Really an icon in the industry. He's coming on as chair of 90.1 right now. Dick said, Mark, you screwed your math up. He said, I know I've got at least 12 million basic model groups, and you've got more combinations and permutations. Right, I said, Dick, does it matter? I got tired of, so basically,
if it's more than 1,000, it's a pain, right? So
right. What DOE said was, if I change from a MERV 11 to a MERV 13 filter, I would have to retest because that would change the efficiency.
Sure.
Of the
unit,
right? So we got to model. We got to do some things. We have to make heat. We can't measure every type of heat recovery. We can't measure every combination permutation. And if we start throwing the VAV boxes on there and the ductwork and the other things that we need to take into effect, there never will be two that are the same. So you could never actually test it. So we got to do modeling. So we got the building modeling. We've got the component modeling. We got to have this math for integration. And we need to do some verification. And so right now there's a lot going on with building modeling. There's tons of people building net zero buildings, and then when they meter them, they don't feel to net zero. And I hear that story over and over again. ASHRAE headquarters is an example. They smartest guys at ASHRAE pulled on all the industry resources, did a net zero new headquarters, but when they start looking at the utility bills, it's just not performing to the model.
Right.
And what that means is the model needs to be tuned up. We got to verify these models. We got to go back and look at them. And then probably the last point, but one of the most important points, is commissioning. So what happens to the building after the engineer leaves, after the contractor leaves, after everybody leaves? And, everybody that's been in this industry for any point in time, the secretary on the 3rd floor is hot and on a hot day, and the maintenance guy goes up and says, if I'd shut that outside air damper, it'd be a lot cooler in the space. So it gets
seen that.
I got a crescent wrench. I can take the actuator loose from shut the outside air damper, and that's the way it runs because he solved today's problem and never went back and unsolved it, right? So you got to keep this stuff. And on top of that, with our best intentions as design engineers or building owners, we think we're using it this way, but life changes, right? And you're using the building the other way. When I worked as a contractor, one of the things I spent a lot of time on was hospitals. I always said, today's lobby is tomorrow's operating suite in a hospital. Hospitals change constantly. There's a constant churn. There are construction in almost every hospital I've ever been into. There's construction going on all the time because they're just changing demands and different things going on. So buildings change. So we've got to keep that up and keep that commissioning and make sure that we understand that we have. And there's kind of this new concept that's been talked about in the last few years. You may have heard people talk about digital twins.
I have not heard that.
Okay. Well, digital twin, with BIM, BIM, this building information management, the Revit and 3D drawings, and where we design buildings and we put all the structure and all the components in there. And of course, the ultimate goal would be to build in all the HVAC equipment and all the thermal performance in there. Can you create a digital model of the building, run simulations on that digital model of the building to help you determine how best to operate that building? So, and they call that digital twins.
Gotcha.
So if we just look back at the energy modeling software, like I said, this stuff has been around since, basically started in the 60s. I started out life in 1980 doing energy studies for a consulting engineering firm. And that was before Blast. That was not before Blast, but Blast really wasn't out there to do that. Blast was, we were running things on punch cards. And then, then you had DOE2 in the 80s, Energy Plus in the 90s. There's been a lot of evolution and interaction there, and it's got better and better and better. But like I said, really the most of the equipment models were created by Blast, and Blast was basically a Department of the Army or Armed Forces program that was put together by the military to analyze their buildings, because the GSA, the General Services Administration, is the largest real estate owner in the world because of all the military bases. So they are a big owner, and they pay a lot of attention to how buildings operate, and so they put Blast together in the 70s. So this Blast program was developed. Some of the people you probably know, Dave Knievel, who retired from AAON a few years ago. Dave was involved in a lot of the early energy modeling. He wrote the Ben method for energy analysis in 1975-ish range. So a lot of those energy models that were models that Dave did in Blast, they're still in there. That's how we're modeling equipment, and it's not any slam on the modeling software guys, but when we only have 4 data points,
right,
and that's all we know about, how do we put something else in there? And that's kind of where that ASHRAE 205 is beginning to come into the realm. So next slide. So 205 has just got released. It's actually released in 2023, so it's brand new, ink still gooey on it, and was basically ASHRAE's attempt at saying, okay, how do we improve these energy models? How do we get this better equipment models for all these components? And the components aren't just the rooftop units, it's the pumps, it's the fans, it's certain things. Physics makes models work really well. We pretty well understand how fans. I talked a lot about that in one of your previous programs.
Yep.
We know fan laws. Fan laws are, they're not suggestions, they're laws. They work. But when you get into latent capacity of a cooling coil, that's a whole lot more complicated.
Right.
It's I can't write a bunch of equations for doing that. So ASHRAE 205 was a way to say, how can we get this map data? How can we encourage manufacturers to get us this map data so we can improve our energy models? Well, I don't want to give my program to Carrier Train in York so that they can reverse engineer and figure out exactly what I'm doing, because there is some competitiveness in the market, and we all want to have our own, own intellectual property. But maybe I could develop a table of my performance. That doesn't tell you how I got there. You can't massage it and necessarily tell how I got there, but you can tell what it is. So what 205 really is these performance tables at these wet bulbs, at this wet bulb, this dry bulb, this indoor, this outdoor condition. So they're multiple dimensional tables. What's the capacity and the efficiency of that piece of equipment or that component? How much power does it use? How much capacity does it use? So if you look at all this, these are some of the tables out of the 205 committee. areas of concern. We've got 4 data points on that chart right now. So, and so they're trying to say, okay, well, if we filled in this middle point and you see this kind of grid of things, of course, the red ones are things that are not possible past the saturation line on a psych chart.
Yeah.
But if we looked at the blue and the green ones, if we had in there, was that good? And then sometimes they operate in the purple and the red. Maybe we need to expand it into there. So that's just part of the discussions that have gone on in 205. But, basically they're looking for people to put these maps together. And,
Gotcha.
and quite frankly, how we're going to put the maps together is we don't have the industry or the world doesn't have enough test lab time. We will never get there to run all those conditions.
Right.
What we have to do is be able to take a piece of equipment or 2 or 3 pieces of equipment across our product line, run it a bunch of different conditions, make sure that we have computer software and our own computer modeling that will match those. And that's where, and it might not be within 5%. That's the other problem that we may run into as we get into this, but maybe 10% is better than nothing, right?
Right.
Maybe we get 10%, maybe we can get 15, whatever it takes. We could run those, develop these models, and then check them at different places with different pieces of equipment. Then the models, the internal software that I don't want to give to anybody else because it's my intellectual property, I can create this map. And then the energy programs will just do linear interpolation in between the data points on this grid. And that's going to be a whole lot better than what we got today.
Right, for sure.
Because today you can't take IPLV or SEER or EER and put it in an energy modeling. It doesn't mean anything.
Right.
It has no effect on how that thing operates in the center of that blue part of that first map I showed you. It because it's not one of those data points.
Right.
It's up there on the edge. It'll tell you only if you hit that happen to hit that point on that edge, which, like you saw in that map, doesn't happen very often. So
yeah.
So like I said, HRI's had this system steering committee. This was the concept. I was one of the charter members of that committee in 2012. Dick Lord, who I talked about earlier, chaired the committee for a very long time. He's been a lot of the driving force behind this, and worked on 205 and 90.1. So what HRI is doing is, we've been working with all the different products in HRI saying, hey guys, all you industry experts go out and figure out how to do this. And now, we're changing refrigerants. We just had an energy efficiency increase. There isn't a lot of bandwidth right now to do a lot of this work, but there is work being done. That's kind of what drove this is the process that drove chillers. That's the reason I said 5 years ago, we kind of went to map ratings, ERVs, heat wheels. Those now are computer-based certifications. So, and the reason chillers are so much easier, water-cooled chillers, we're just looking at the water. We're not looking at the cooling tower. So there's no wet bulb involved.
Right.
And, it's, capacity is 500 times the GPM times the delta T. Now, you can change fluids and change those numbers a little bit, change the 500 a little bit, but it's pretty simple math. Pretty predictive. So then you just got to work on fluid to fluid heat transfer in there, or on an air cooled chiller, it's a little bit harder, but still they're typically, it's air cooled and water cooled chillers. I didn't say evap cooled chillers because that gets harder. Because whenever you throw that latent load in there, the complexity of the math and the modeling gets harder.
Right, for sure.
So we really haven't figured out what we're doing with rooftop units yet. Anything that has a latent load on it, coils.
Yep.
Those kind of things. There are modeling software out there. There's things that people have done with them. But there again, HRI always certified coils. It's a very narrow range. Now we need to expand that range. So,
yep.
So that's kind of the modeling part. Let's get the best equipment. Can we do? Okay, now how do we control that equipment? That's where I think one of the things you got to understand about what we're doing today with prescriptive measures is I'm running a piece of equipment at a condition for an hour to get a single data point efficiency and capacity reading. There's no controls involved in that piece of equipment. It is locked in that position.
Gotcha.
And so controls, we know, are going to have a big difference on how the unit works. Yeah. In today's world, we live in this variable speed world, right? We have variable speed condenser fans, variable speed evaporator fans, variable speed compressors, variable speed chill water pumps. Everything's variable. At any given set of load conditions, there's probably one speed for each one of those variable speed components that will use the least amount of energy. Figuring that out is hard, because if you change the outside air temperature, you change the outside air humidity, or change the indoor air humidity, that speed and everything's going to shift around a little bit, and it's not directly, so there's a lot of people talking now about even AI, artificial intelligence types, neural networks. Can we build control? That's entering into the control system world. Hey, can this building self-learn by saying, hey, last time I ran at this point, I ran this, and this, and it used this much energy, and now I'm running this, and that, and it uses less energy. Let's eliminate that one and let's move it a little further that. So can they learn as they go along? So there's lots of opportunities and controls. So for young people entering the industry, when I talk to student groups and stuff, I say, hey, energy modeling and controls and commissioning. That's where the future. That's the future. It's where it's got to be. And and the other part of this is now we got smart grid. We've got utility companies that are saying, hey, we're really trying to save greenhouse gas. What I want to do is I want to turn whatever I'm using to run my generation, solar, wind, hydro, nuclear, natural gas, whatever it is, and I want to run it at its peak efficiency all the time. So I want to be able to control the demand for power into the building. So what can I do to control the demand? Can I talk to some of the HVAC units and say, hey, I'm getting close to where I always remember the scene in Christmas Vacation where Griswold turns his lights on and they have to throw the switch on the nuclear power plant. By the way, that would have been a gas turbine compressor. They don't fire up a nuclear power plant for peak load, but that's beside the point. But that's what happens when you hit those peak loads. Right. Or do I call out and say, hey, would you let your temperature come up 3 or 4 degrees in your house, for a couple of hours and not have to turn on the nuclear power plant or the new gas compressor by talking the equipment. So building integration, and even inside the building, how much hot water am I using? How much, can I recover heat that I'm expelling from my condensers to hot water? This is where heat pumps and water source heat pumps and heat pump chillers and all this stuff that is getting a lot of attention these days. But you have to look at it on a whole. So, so you can't just look at the efficiency of the heat pump chiller if you're not looking at if you're making domestic hot water with it, if you're not counting for the energy you would have used to make the hot water if you weren't using that heat pump.
Right, exactly.
So all these systems integrate. And one of the many committees I've served on at ASHRAE was the Tall Buildings Committee. I always called it my play committee because how many tall buildings does anybody get to build? But but they're really cool when somebody builds them, and they're incredibly mechanically complicated to build a 100-story building. And could we use the chill water system for sprinkler system? Why not? Other than the fire marshals freak out because they don't want anybody touching their system. But things like that, those kind of integration things, can we do to make more efficient? So those opportunities going forward, I always say the winners are going to be those those people that can, embrace, innovate, integrate all that together to see the whole picture, the people that can move toward this. But it's sometimes it feels like in our industry, and I'm sure in every industry, you got to wait for the old guys to die off before you can make a change, because we all get set in our ways of this is the way we've always done it. I did this way.
Yeah.
So many years ago, but this is a big change from changing from these prescriptive, and the interesting thing is you look around the Systems Steer Committee at HRI, it's a bunch of old guys, right? Yeah. but a bunch of old guys have been around a long time and said, hey, we've been doing this our whole lives. It ain't working.
Yeah. Our willingness to take risks definitely diminishes as we get older. That's for sure.
But
totally understand it.
So, there's lots of things to do there. And then we have to convince everybody to, well, if we do this, we will save energy. Trust us. You don't have to write a law. You don't over-regulate us. Don't regulate every component in that system just because you can, because I'm pretty sure that's where I said you have to be able to look at the give and take and the integration. A lot of the regulatory reforms, the new FEI fan metric that is in 90, well, it's not new. It's been around since it's been in 90.1 since 2019, but it's beginning to get a lot of play right now. People are just now kind of getting used to it and hearing about it. It's really a rating of that fan at peak load. And in a VAV system, it'll walk out of that peak load. It's kind of like that cloud you saw. You're not going to be operating at that point all the way down the fan curve. When that fan's running at 75% down in the middle of the blue cloud, 75% capacity, you're not going to have the efficiency represented by that FEI that you selected, that you regulate that fan that it has to be at. So
right.
So if you don't look at all this interaction piece, if you don't look at the whole building, you don't get the whole picture, I guess is the point. So
absolutely.
I'm not smart enough to solve this. I'm way too old to solve all this because it's going to take a long time. But there are people out there that do that.
You're raising awareness and pointing.
I'm raising awareness.
And
I
right
think it's a huge opportunity to go out and do this. And right now from a manufacturer standpoint, trying to figure out how to get these maps done is kind of like the scary 500-pound gorilla sitting in the corner of the room that tell you, well, we're not really doing anything yet. We're just scratching our heads saying, well, how would we even start? But what will drive that is people saying, hey, I need it. And
right.
And ASHRAE 205 is one part of it, because you're going to see people start building the 205 tables into Energy Plus or whoever's energy program. And if we incent people to save energy in buildings and look at whole building energy modeling, that's kind of what, net zero buildings don't use zero energy any point in time, usually.
Right.
They're either making it or saving it, but they're never at zero, right?
Absolutely.
They don't run off the grid.
That's right. That's right.
Typically.
Yeah.
That's a different thing. So
I got a few friends with cabins up here that run off the grid, but that's a whole different story when you got a commercial building, and that's
and they have a certain amount of inconvenience to do that, right?
Hey, I'm not off the grid. I can tell you that. I have no desire to do that at all. But your
kids don't want to be off the grid, right?
No, their dad doesn't want to be off the grid either. That's for sure. So, awesome. Well, Mark, I'm going to go ahead and wrap this up. Thank you so much.
Okay.
This was some great information here, and so thanks everybody for joining us today. If you would like this video, whether you're watching it on YouTube or you're watching on LinkedIn, we would greatly appreciate that. If you want to share it, that's great too. You can get your PDH credit at my email address or your PDH certificate at tmormino@insightUSA.com. If you'd like to connect to our podcast, you can zap the old QR code in the upper corner there, or reach out to me and I could send you the link. to the podcast. And Mark and I will stick around and answer a few questions here. But thank you all so much for joining us. And thank you, Mark, for the great presentation.
All right.
Awesome. You did a great job. There's one question in the chat here.
This is the hard part. I don't know whether I'll be able to answer all the questions.
No, there's just one here real quick. It says, Eric is asking, is there a tool available that can use hourly building load data, say from eQuest, to select equipment such that the load matches the IPLV or efficiency curve?
I don't know. I understand that question.
Yeah, I'm not sure. So yeah, Eric, email me.
That IPLV and efficiency curve is what it is. So it's,
yeah.
What your eQuest is going to give you is those blue dots and red dots.
That's the building load. Yeah, it's kind of
that's the building load.
Things.
So
yeah.
So I mean, translating from that IPLV into that blue part is the 205 maps that today we kind of have for chillers, although we don't have the cooling tower side of it.
Mm-hmm.
And is the energy modeling good enough for the cooling tower side? That's outside my realm of expertise. Probably not, I'd guess. But you really have to look at the pump energy, and I've spent a good part of my life looking at air cooled versus water cooled chillers, and which one's more efficient depends on how far the cooling tower is and the elevation of the cooling tower from the chiller. A lot of times, because air cool can be more efficient than water cooled if you take into account the pumping power and the cooling tower energy.
Yeah.
So it depends. So I guess that's the answer to the question. It depends.
I think I was 2 weeks into the industry when I heard "it depends" about 400 times. It's like the first thing they teach you when you're new to this industry. And often I get asked questions and I'll go, I'll give you this answer and you're going to hear it a million times. It depends. And then, 15, 20 minutes later, you've got 3 options and the pros and cons of each and yada, yada, yada. So,
I mean, the really important part about the modeling, the thing that we got to get the guys that are working on modeling is we've got to validate the models against real buildings. So we need to build buildings. We need to model buildings. We need to build buildings. We need to feed the weather data, hourly weather data recorded on that building back into the model and see where we have deficiencies and keep working on that. And so the building modeling guys aren't done, and I've always said, in my career, me and Dave Knievel, who you probably have met, really smart guy, but Dave's been a modeler. He was an early modeler, worked on Blast, and I've said I've had a lifelong argument with Dave because he keeps saying that my reality is wrong because it doesn't agree with his model. And I keep saying his model's wrong because it doesn't agree with reality. But
that's right.
But there's a lot of that goes on, and reality has data scatter in it. I measure it 4 times, get 4 different answers within a range. Yeah. Hopefully.
Yeah, often I'll be on a job site and we'll all have our own little meter. We'll be reading some point and we'll all have a different point. One guy's way out here, one guy's way out here, and the 2 are kind of close enough to say, okay, we guess it's
it must be in here, right?
Yeah.
So it's
awesome. Well, great.
The modeling guys can get you to the 6 decimal point, but I'm not sure it's right.
Exactly.
So
okay, good. Well, thank you, Mark. If you can hang out here for a few minutes. And we appreciate it. And thank you all again so much for joining us. We appreciate you. We'll catch you next time.
All right.